A large brain is a hallmark of hominids or human descendants, but does a bigger brain size mean that a species is more intelligent? Dr. John Hawks, paleoanthropologist at the University of Wisconsin-Madison, answers this question.
So, brain size and intelligence. We think of intelligence, and that means sort of how smart you are. But there are so many different ways of behaving that factor into this. Even when we look at today's humans and we say, I give them an intelligence test. Those of you who've taken a test like this know that there are different tests. They're testing how good are you at moving blocks, and how good are you at finishing a series of cartoons, and how good are you at coming up with a word. You know, it's different kinds of behavior that are factoring into this. When we look at today's people, huge range of variation in how big your brain is. Normal people that have normal development, normal brain size, have brains as small as 800, 900 cubic centimeters and as large as 2,000, 2,200 cubic centimeters, right? So that's a huge range of variation. Some variation in size, if you take people, measure their brain size, put them in, give them tests, you could say, well, there is some variation based on size and how some test performances happen. But the very fact that men and women do not differ in test outcomes on average, and men and women differ in brain size on average, tells you that brain size is not any kind of simple measure of, and in fact, all the correlations with any kind of tests within sex are kind of low correlations.
As Dr. Hawks said, the relationship between brain size and intelligence is complicated. Though one is not always correlated with the other, brain size did increase overall when hominids became bipedal. Dr. Bernard Zipfel, curator of the fossil vault at the University of the Witwatersrand in South Africa, describes why hominid brain size increased due to bipedalism, or walking upright.
We first became bipedal. In other words, our feet evolved to a point where they allowed us to walk upright rather than using our lower limbs to climb trees. And at that point, it freed up our hands so that we could start doing things with our hands other than locomotion or movement. We could start examining items. We could start experimenting with things like tools. We could hold a baby and walk upright. And by doing that, it allowed our brain to be more active and essentially interact with these activities we're now doing with our hands. And that's when our brains started getting bigger. So it seems that we became bipedal first, walking upright, and then our brains became bigger, and then we became intelligent apes, which is what we essentially are. And we then developed these larger brains, much larger than any of the other primates, and very expensive brains that had the capacity of developing technologies, developing culture, developing civilization, and to what we are today.
In summary, hominid brain size increased after becoming bipedal because their hands were freed up to use tools, hold objects, and participate in cultural behaviors. If you would like to learn more about how bipedalism affected hominids, watch our video titled, Does Walking Upright Matter? Dr. Lee Berger, paleoanthropologist at the University of Witwatersrand in South Africa, describes how early distinctions between Homo and Australopithecines, like brain size, have become blurred as scientists have come to learn more about how these two classes are interconnected.
Right. So that used to be a really easy answer, the idea of what is Homo and what's Australopithecus. And if it were 10 years ago or so, I'd answer that very quickly about different morphological characteristics that clearly define the two groups. But in the last decade or so, largely because of the discoveries made, a lot of them right here, it's become a lot less clear of what exactly is the definition of Homo and what's the definition of Australopithecine. Typically, the way that we are broadly looking at it is that Homo is a grade that is largely the adaptation that we humans have. And tends to include things like a larger brain, encephalization, a adaptation with tools, and the reduction in tooth size, and changes like that.
So when you say larger and reduction, is there a standard line? How do we decide what's larger and what's...
All of that's the big problem right now, because what has happened in the last decade is we've discovered species that violate that completely. One of them is Homo naledi, which was recovered right here, which is a species when you first look at it, and when lots of scientists first looked at it, thought it should be 2 to 3 million years old because of its anatomy, because it had a tiny brain. It has morphology that looks a lot like an early Homo erectus or a Homo habilis or things like that, which typically you would put back at 1.9, 2 million, maybe even 2.5 million years old. But had characters of it that looked much later too, that you would see in more derived or advanced species like humans. It's this mosaic or combination of features, and of course it exists very late in time though. Only say 200,000 to 300,000 years ago. And so it's species like that which have caused us to pause on the easy answer of, in what genus you are, and then also begin, I think a lot of us are beginning to ask, are those really useful terms? Is it that important to divide these things up? Because what we're finding is that old t-shirt model of human evolution, the idea that, one species gives rise to another, gives rise to another, gives rise to another, ever advancing towards modern humans, that's just simply not true.
As Dr. Berger explained, the extinction of smaller-brained Homo species didn't just happen immediately, it happened gradually over time, creating a long period of time when small-brained bipedal specimens roamed the earth. A good example of the merging of Homo and Australopithecus, more ape-like ancestors, is the Taung child. This specimen was originally thought to be an ape due to the small size of its brain, but many other characteristics, such as human-like teeth and an upright stature, proved that the Taung child was indeed part of the ancient human genus, even though its brain was quite small. Overall, brain size does not strictly predict intelligence or relationships between humans today and our ancient relatives. It was our ancient ancestors' change to bipedalism that freed our hands to explore and grow into a species with culture and tools. Because of the switch to bipedalism, our brain size increased. The Taung child is hopefully one of many more discoveries that will fill in the gaps between our small-brained, non-bipedal ancestors and us as modern, bigger-brained bipeds.